Hey everybody, today is Monday, 21st of June 2021. Let's continue with solve problems, fields and waves in communication electronics. Um, we're still working on chapter 1. Uh, Topic still about potential, electric fields, boundary conditions. Problem 1.18a proof that the light charge and its image as the described for a conducting cylinder in example 1.18c will give constant potential along cylindrical surface at radius a in the absence of the conductor cylinder. Sorry. Okay, take a look at the picture here. You have a conducting cylinder with radius a, and you have a point charge q with distance r from the center of the sphere. We're going to apply the image of a light charge in a cylinder. You have to keep in mind that when you have the point charge q with distance r from the center of the sphere, that means you can create just like the image here, charge q prime. That's going to be negative qa over r. You have the opposite charge, and with the distance from the center, a square over r, so that's related to a, with which is the radius of the sphere, and also r, which is the distance, the point charge q from the center of the sphere. And after that, you can use the superposition to find the potential. Okay, this one is asked you to prove the light charge as its image will give you a constant potential. Okay, let's get started. So they ask you to prove that VR equal to Q, to prove, okay, sorry. And you start with the equation of the potential VR equal to Q over 4 pi epsilon R. That's the potential from a point charge with a distance r from the center of the sphere. By superposition, your VR going to be the voltage from Q and the voltage from the Q prime. So simply you add them up, and that's give you a VR equal to 0, or your VR is constant. Okay, that's the problem 1.18a. Let's see here. Okay, let's move to problem 1.18d. For a point charge q lying in a dielectric epsilon 1 distance d, this is the xy plane, and this one is boundary. You have dielectric 2 and dielectric 1 with the dielectric permittivity epsilon 1 and epsilon 2, and you have x equal to 0, separating two planes. You have the point charge q with the distance d along the x-axis above the boundary. You can simplify by that you were to compare that the given charge plus an image charge. So you have a q prime in the with a distance the negative d from the boundary, and that q prime equal to q epsilon 1 minus epsilon 2 divided by epsilon 1 plus epsilon 2. But you have both dielectrics constant of permittivity equal, which is the epsilon 1 and epsilon 1. And also for x less than 0, I mean in the term you're looking for the potential. For x less than 0, that means you have the charge to q epsilon 2 over epsilon 1 plus epsilon 2, and with the permittivity epsilon 2. Okay. What we are looking for, that's you to show that these images satisfy the required continuity relations at the dielectric boundary. So what is the continuity? The continuity is that you have dn1 equal to dn2. Okay, that's the boundary conditions. What is n? N is mean in the normal to the boundary or in x direction. And also you have et1 equal to e2. This is the electric field. That means T represent transverse electric field of in the y direction, but we're going to apply dn1 equal to dn2. That's the continuity. Okay, so you need to pick up two regions, one for x greater than 0 and the other one is x less than 0. For x greater than 0, you pick up these pictures. So by superposition, phi1 going to be the potential from the point charge q and the potential from the point charge q prime, or the image charge. So by applying sorry, phi r equal to q over 4 pi epsilon r, you end up with phi1 equal to q over 4 pi epsilon 1 multiplied by r, which is the x minus d plus y squared plus z squared, and 1.5 plus the second charge q prime, which is the q epsilon 1 minus epsilon 2 divided by epsilon 1 plus epsilon 2, and divided by 4 pi epsilon 1, and then when you have x greater than 0, so this one become x plus d squared plus y squared plus z squared 1.5. Now for x less than 0, your phi2 is equal to the chart to Q epsilon 2 divided by epsilon 1 plus epsilon 2 and divided by 4 pi epsilon 2, because you have here epsilon 2, right? And then multiply by x minus d square plus z square plus z square, because your x is less than 0. So you have both phi 1 and phi 2 for x greater than 0 and x less than 0. So this one is x greater than 0, and this one x less than 0. And you apply boundary condition dn1 equal to dn2, or your d equal to epsilon n, epsilon e, and e equal to grad phi, right? And you consider only in the x direction here, in the x component, right? Because it's normal to the boundary. So you simply differentiate phi with respect to x, and you take x equal to 0. You can work out, differentiate of phi 1 and differentiate of phi 2 with respect to x. Finally, you this is the e in 1 here, equal to this equation. And so you have d in 1, e d in 1, and for d in 2 you have this term. This show that both boundary conditions are satisfied, because these two terms are equal. Okay? This is negative q or d epsilon 2 divided by 2 pi epsilon 1 plus epsilon 2 and multiplied by d squared plus y squared plus z squared. Okay, so that's the problem 1.18d. So you apply the image charge for the problem. Next, here's the problem 1.18g. Find the potential at all points outside the conducting sphere of radius a. So the sphere has the radius a, is held at potential phi 0 when a point charge q is located distance d from the center of the sphere, or a less than d. You have the point charge at the distance d from the center of the sphere. For the problem, in general, you have the point charge q, and it's easy for you to find the potential at point q1, at the point charge q1. But for the problem, they have conditioned that at the surface of the sphere, the potential is equal to phi 0. So you need to add them up and ask you to find phi r at arbitrary point r. Also, you apply the image charge. So you have your q2. First, we not consider phi 0 yet, okay? But we are looking for superposition. We're going to apply the superposition method to find phi r. For the image charge, your q2 is going to be negative q a over d, when a is the radius of the sphere, and d is the distance of the point chart q1 to the center of the sphere, and that is the distance, the a squared over d. Now, to produce phi 0 on the spherical surface, we must add chart q3 at the center of the sphere. Now, look at this equation. Okay. You have the q3 at the center of the sphere, and you're looking for the potential at the surface. And that's the potential at the surface going to be phi 0 equal to q3 divided by 4 pi epsilon a. Straightforward, right? A is the radius of the sphere. Then your q3 equal to phi 0, 4 pi epsilon a. Then by superposition, the potential phi r going to be the potential from q. Sorry, just put this one as q. And q2 and q3. So the first one is the potential at the distance r from the center is the q divided by 4 pi epsilon r1. This is your r1. Or you take a look at from the picture here in the term of rectangular coordinate x, y, z. This is your q. So this is the VR that you're looking for. And plus the potential from q2, which is the negative q a over r. Sorry, a over d from the center, right, of the sphere. Divided 4 pi epsilon r2. This is your r2. And also your q3, sorry, the potential from the chart q3 equal to q3 divided by 4 pi epsilon r. Right? You measure from the center. So you add them up. Okay, so your phi r, that's going to be equal to q divided by 4 pi epsilon r1 minus q a over d over 4 pi epsilon r2 plus a phi 0 over r. And from the picture, by cosine law, your r1 going to be equal r squared plus d squared minus 2 dr cosine theta. What about r2? R2 is going to be r squared plus a over d squared. So this is the distance, right? And you pick up this triangle. That's your R2. So R2 equal to square root of r squared plus a squared over d, because the q2 is at position a squared over d from the center of the sphere, minus 2a squared r cosine theta over d. So that's this your potential at r on the xyz plane, with the condition that the potential at the surface of the sphere equal to phi 0. That's problem 1.18 G. Problem 1.122D show that the equality of energies found using equation 1.225 and 6 from a spherical volume of a charge of radius A and charge density rho coulomb per cubic meter. I pick up equation 1.225 from the book. That's the energy stored in the electric field. That's equal to 1 over 2 integration volume integral rho phi dV. And from equation 1.226 UE equal to 1 over 2 volume integral of d dot E dV, where D is the electric flux density vector and E is the electric field vector. So we apply Gauss' law. Closed surface integral d dot ds equal to q enclosed. You need to consider two different regions. One is r less than a and r greater than a. For r less than a, by applying Gauss' law, dr, okay, because the d has the component or the in the r direction, so you put this one as dr. And for the s, that's also going to the same direction as the radius, component. So d dot ds simply become a dr multiplied by the area of the the area, because that's ds, and the area of the sphere with radius r equal to 4 pi r squared. That's equal to q enclosed. That means the charge density by volume multiplied by volume of the sphere, and the volume of the sphere is 4 pi r squared, 4 pi r to the cube divided by 3. You multiply by rho, you have a q enclosed. And r square cancel r square, so you end up with rho r over 3 for dr, or that's equal to epsilon er. Now for r greater than a, but you apply Gauss' law, and for the chart or the q enclosed, that's going to be rho multiplied by the volume of the sphere. So you put, instead of you put r, you put a to the cube, and you have dr equal to rho a to the cube divided by 3r squared. That's also equal to epsilon er. Okay, now we have to prove that by applying equation 1.1225 or equation 1.226 will give the same result. First, let's do equation 1.225. You need to consider both r greater than a and r less than a. So you need phi, or the potential, and the potential equal to a negative line integral er dr, or E dot dl, right? But since your electric field has the radius component, so you put this one as er and dr prime. You need to integrate from r, because you put r greater than a, so you integrate from infinity to r. Okay, you can work out the math by yourself. You end up with phi r for r greater than a equal to rho a to the cube divided by 3 epsilon r. Now for r less than a, you integrate from a to r, but you need to plus phi a because you have the potential also at the surface. But for this one, for phi at infinity, your potential is equal to 0, so you don't have this term. But for r less than a, you need to take into account of phi a. What is phi a? Well, you take a look at the previous integration for r greater than a. You put r equal to a here, you end up with phi a. So your phi a equal to rho a to the second divided by 3 epsilon r. This is your phi a. Okay. So again, you do integration. You have your phi r for r for r less than a equal to rho a to the second divided by 2 epsilon minus rho r to the second divided by 6 epsilon. And you back to the equation here. Since you already have rho, but rho exists from r less than a, right, inside the sphere. So for r greater than a, you don't have rho, or rho equal to 0. So when you apply the equation ue equal to 1 over 2, you simply integrate from 0 to a only, not to infinity, and rho phi dphi. And since you're working on r less than a, you need to pick up phi from this case. Okay, this is r less than a. By integration, you end up with ue equal to 4 pi rho square a to the 5th divided by 15 epsilon. Now let's check out ue from the other equation, or 1.126. ue equal to 1 over 2 volume integral of d dot e dv. Since we already have e for both cases, that's r less than a and r greater than a, and you also have your potential phi r for r greater than a and phi r for r less than a. Then you do the integration, okay, from 0 to a and a to infinity. By integration, you have ue equal to 4 pi rho square a to the 5th over 15. Show ue from 1 over 2 volume integral of rho phi dv equal to 1 over 2 volume integral d dot e. So that's the problem number 1.22d. Okay, so this is for the series, and we will continue more problems in the next series. Okay.